Now let us talk about this concept of crack resistance. Okay. So here you have two curves. The left hand side is the crack resistance curve, or it is also called R curve for a ductile material, and the right hand side you have an R curve for a brittle material. Okay. So this R curve is nothing but it's a material property. It is like the critical energy release rate. So this is resistance, right, offered by the material for the crack growth. That is what this is representing. Now for a ductile material, what happens is, for a brittle material first, the critical energy release rate does not change as crack grows. It is constant. So that is why for a given up to certain, for a given material up to you have a crack length. So let us say this is A naught. If your crack length is below A naught, okay, that crack does not propagate. The moment the crack length is below A naught, and if you are, so let us say this is one loading curve which gives you energy release rate G, so corresponding to a applied load sigma. Let us say you have another loading curve, this is corresponding to sigma 2. You are applying a load sigma 2 that corresponds to this evolution of G. We have calculated G, remember. The G can be calculated, and let us assume that G varies like that for a given sigma 2. And all the time, now, for instance, you take a crack here, the crack length, for this particular crack length, you have to see whether crack is going to catastrophically propagate or not. The condition, this is your crack resistance curve. The crack propagates only when this energy G is greater than R. R is your resistance or the material property. Here it is less than that, and hence it will not propagate. This guy is your R. The one is in red. I should not have chosen red color. Let me see if I can change my color. Yes. So let me say this is A naught, and let me draw this curve. And this is the first black curve is corresponding to one particular load. One particular load, and that gives me that G evolution. If let us say this is my another particular load, say sigma 2, that gives me another G evolution. This is the evolution of G as a function of crack length. And now you see that for any material, for any value of G, if my crack length is less than A0, there is no resistance, right? You do not see the red curve. That means if my crack length is less than A0, my crack will never propagate. It is not a critical crack anymore. The moment my crack length is greater than A0, then will the crack always propagate? Not necessarily. If my load is so low that it is like this, so my G value, say let us say I am calling it as G2, is always less than R, right? Since it is less than R, the crack will not propagate. So here, even here, the crack, you may have an increased length of the crack, say A1, but the crack will not catastrophically propagate. Yes. Yes, yes. Okay. Is that clear? But here the point is the resistance is not changing. The R curve is a constant curve. Now come to ductile materials. It is typical in ductile materials because of the plasticity that is prevalent ahead of the crack tip. The resistance changes as a function of crack length. As your crack grows more and more, your crack tip becomes blunter. If the crack tip becomes blunt, then you have more resistance to crack growth. And that is why here the red curve in this figure shows an increased R curve, right? The crack resistance curve is increasing. That means the resistance is increasing. Now you see, if you are applying a load sigma 1 up to A naught, of course there is no crack growth at all. But A naught, this is when the crack actually starts growing. But as soon as you cross this guy, immediately the resistance is more than this guy. And hence the A1, it will be there at A1 and then it will not grow. Now come to sigma 2. When this guy is sigma 2, you see that the crack starts growing up to A1 and then it stops, right? Because A0 is the initial crack. You have initially A0 crack, but you are applying a sigma 2 load, and when this guy hits the G curve, that is when G became equal to R, and hence crack has to propagate. So crack suddenly propagates from A0, but then the moment crack reaches the length A1 under the load sigma 2, suddenly what happened? R became more, and hence it cannot catastrophically propagate. It starts from A0 and grows up to A1 and stops there, because beyond A1 R is greater than G2. Is that clear? Now the moment your sigma curve or G curve becomes tangent to your R curve, and that is when you will have critical crack growth, because the rate of change of G with respect to A becomes larger than rate of change of R with respect to A beyond that point, and that is when the crack suddenly propagates. That means that is when you will have brittle fracture. The ductile material breaks like a brittle material beyond this point. That is when, yeah. So conditions for unstable crack growth: first, G should be greater than R, and dG by dA should be greater than dR by dA. Is that clear? So that is typically the case in ductile materials. For brittle materials, you will not have this R curve changing, or the resistance will not increase as the crack length increases, and hence that is precisely the reason why whenever you throw a stone on a glass, the glass breaks all of a sudden, right? If you have a small crack, it zips through, right? That is because you have no increased R value. But if you have a reinforcement to the glass, right? So typically the car windshields and all, they will have some reinforcement within, right? So they don't break like the glass that you would break on your window, right? So there will be, the crack propagates up to certain distance and then it stops. Although from the design perspective, you have to replace the windshield, but it is not going to break like the window glass breaks. That is because there is some reinforcement which is sort of offering the R curve. The R curve of that material is actually increasing as the crack is growing. Can you see that? Okay. Any questions here? No questions. Good. Now, how does the stress state ahead of a crack tip look like? You can actually do a elasticity course and derive this formula, but in this class we are not doing that. I am only giving you the formula, how do they look like. So let us say this is your crack in an infinite body subjected to far field stress sigma, and then crack length is 2a. Now if you define a polar coordinate system at the crack tip, r and theta, at any position r comma theta, the stresses sigma 11, sigma 22, sigma 12. This is sigma 11, sigma 22 is this, sigma 11 is this direction, sigma 12 is your shear stress, is given by this. That depends on obviously size of the crack, A, far field applied stress sigma, and the state of stress changes from crack tip to the far away. What happens near the crack tip, by the way? What is the value of R near the crack tip? Infinity. Sorry, R is 0, and hence as a result sigma 11 will become infinity. So you would predict infinite stresses ahead of the crack tip. If you are predicting infinite stresses ahead of the crack tip, as we have discussed in the previous class, if you take a material, if you already have a crack, you really don't need to apply a far field stress. You just blow, then it should break apart, because the stresses are going to be infinite just by a mere blowing. But that is not what is going to happen in the real materials. That is because real materials are not going to have sharp cracks. You are going to have some crack blunting, but this is for perfectly sharp crack. This solution is for perfectly sharp crack. The moment you have plasticity, you will have a local plastic deformation, and then there will be local crack blunting. So you need to take that into account when we are doing that. But this is a solution assuming pure linear elasticity. Okay? All right. Now, if you carefully look at it, your stress depends on sigma, applied stress, and the crack size. So there are two variables, applied stress and crack size A, right. So now you can actually, so this you can put them together and define a new variable called K1, and the new variable K1 is equal to sigma root pi A. Whatever you have here, this entire term is defined as K1, and this guy is called stress intensity factor. This is called stress and it has a strange units. The SI units of this guy is MPa root meter, because sigma is MPa and root meter, right. So the K1 sort of represents the vulnerability of a crack, how vulnerable this crack for propagation. So when the stress intensity factor ahead of a crack tip, at the crack tip, reaches some critical value, that is when crack propagates. So the condition is when K1 becomes equal to K1C. Why 1? Again, mode 1 stress intensity factor. Similarly, you will have mode 2 stress intensity factor, mode 3 stress intensity factor, they can be defined, and they will not be same as mode 1 stress intensity factor. Similarly, K1 when it becomes equal to some critical value K1C, that is when crack propagates. Until then crack does not propagate, and this one is a material property again like G1C. G1C is our critical energy release rate. This is critical stress intensity factor, or also called fracture toughness. So after writing this K1, then you can write sigma 11, sigma 22, sigma 12 in terms of K1, because your far field stress is applied perpendicular to the crack face, and hence it is mode 1 loading, and the displacements ahead of the crack tip can also be defined like that. You can actually, if you know stresses, you know the stress strain relations, right? How to write stress strain relations? Do we know or we don't know? Epsilon xx is equal to sigma xx by E minus nu times sigma yy plus sigma zz by E, and so on. So you can actually calculate strains. By knowing strains, if you integrate strains, what will you get? What will you get if you integrate strains? What is strain? How do you define epsilon xx? For small strains, it is one dimensional, u is the displacement in x direction, right? Isn't it the definition of strain? Yeah, u is the displacement. That is the differential element if you take, then that is the real definition of strain, not your, yeah, that is also okay, but this is the proper way to define strain. Then how will you get displacement? You integrate strain, you will get the displacements and apply boundary conditions, right? And you do that, then you get the displacements, all right? However, this stress intensity factor that we have defined strongly depends on the geometry. So the K1, the way that we have defined, is true only for infinite plate geometry. That means the size of your crack 2A is much larger than the size of the plate, but not necessarily you have that sort of a condition all the time. Then you need to account for that violation of the constraint, that the size of the crack being much smaller than the plate size. If the size of the crack is comparable to the plate size, then you have to add a geometric factor to the definition of your K1, and that geometry factor is given by this beta. So then K1 will become equal to beta times sigma root pi a. Okay. So here is an example problem. So you have a wall of thickness 12 mm whose flaw size 5 mm deep. So you have a crack of 5 mm deep. You need to determine if the wall will support a tensile load of 172 MPa. So if this is 172 sigma infinity MPa, you need to check whether this will support that or not. That means whether the crack will propagate or not. And the K1C for the material is 24 MPa root meter. That is given. Then your K1 equal to normally sigma root pi a, but here the flaw is 5 mm and thickness is 12 mm. So they are comparable. So you cannot neglect the geometry effect. So the geometry effect is given by this factor, under root secant to pi by 2t. That is your geometric factor. You add that geometric factor and calculate K1. So the formula that we have is for crack length of 2a, right? So that is how you take a symmetry thing and then you will add that one. So this is exactly similar to what the problem that we have looked at when we have redefined K1, and then this is your K1 formula. Failure occurs if K1 is greater than K1C. So now we need to calculate K1. 172 is the far field stress. 2a is total distance, but a is your flaw size. So that is 5, and you know what is a and what is t, and then 27.17. What is your K1C? 24 MPa root meter, and hence this is larger than K1C, and hence your crack propagates. So it cannot support that load. All right. So we have talked about two quantities: energy release rate and stress intensity factor. So there is a relation between energy release rate and stress intensity factor, that is G1 equal to K1 square by E. G1 is the energy release rate, K1 is the stress intensity factor. But the stress intensity factor, where did we define? For a given crack length. So that means it is a local quantity. When we are talking about energy release rate, we are talking about the energy, total energy of the entire component, right? And hence it is a global quantity. And there is a relation between, so how this K at the crack that we have defined at the crack is defined, is evolving, that changes the way that G evolves. So they are directly correlated, G and K1, right? Anything else? Any questions? G equal to? No. G will actually, when we are talking about K1, you are talking about the local, you are talking about the crack tip. From the crack tip, so the way the crack tip is defined, K1, the another definition I think I have not, yeah. The definition of K1 is sigma 22, that the far field stress times root 2 pi r at theta equal to 0. So that means we are actually looking close to the crack tip. So we are actually evaluating the behavior of the crack locally, what is the status of them. Whereas G is telling you the energy. Energy is the total quantity of the body that we are talking about. So what is the total energy release rate? We are not really working, the energy release rate is calculated from total strain energy and the work potential, right? That is how we have defined. So we have written G equal to minus d pi by dA, and pi is your total energy of the component. That is when the G is called a global quantity, K is called a local quantity. All right. All right. So the purpose of this module on fracture mechanics is in no way to give you complete understanding of fracture mechanics, but to educate you on the two concepts, the strain energy release rate and stress intensity factor, and to make sure that you understand that the crack propagates when the stress intensity factor exceeds the fracture toughness of the material, or energy release rate exceeds the critical energy release rate. both are equivalent. Whether you say my energy crack propagates, my energy release rate increases, goes beyond critical energy release rate, or when I say my stress intensity factor becomes equal to or greater than my fracture toughness of the material. Okay, both of them are equivalent. So that's all. But if you want more knowledge about fracture mechanics, that can only be done by taking a serious course in that area. All right. Okay.